All right. Can you see the slides? All right, good. So we have covered sputtering, a little bit of sputtering last week. So we learned that sputtering is another PVD process, physical vapor deposition process. So you need to have this environment, as what you can see on the slides. You need to have plasma, you need to have vacuum, ambient. You need to have argon plasma. You need to have sputtering target. You need to have your substrate for deposition. So it can be silicon, it can be glass, it can be plastic, it can be a range of other materials as well. So to be able to do the deposition, to do the sputtering process, first we need to vacuum the chamber down to about -5 torr, and then we need to inject the argon gas, and then that will bring the pressure back to around -3, so that will be millitorr. So then we initiate the formation of plasma. So you're gonna see colors of your plasma based on the gas that we use, and the typical one is argon, right? So we've seen on the YouTube last time the color of the argon plasma, and then we're gonna have our sputtering process started. So we normally have our mechanical shutter on top of the target to block the sputtering. Well, the sputtering runs, but it's not everywhere yet. So to block the process, or you can in fact do a cleaning of the target before the actual deposition, so you can actually sputter the material, but you block the deposition from reaching your substrate by having a mechanical shutter. So that means the substrate is actually sputtered, but there is no deposition on the substrate. And then the moment you open the shutter, so you will see the crystal monitor reading deposition rate, right? The deposition rate typically nanometer per minute, nanometer per second, so on and so forth. And then this the thickness will start building on your substrate. For example, if you want to deposit RTO or zinc oxide or silicon or aluminium or silver and some other materials. So it involves a momentum transfer from the incident atoms to the surface atoms. So basically, you need to use argon ions at a high energy, bombard the target material in order for the material to be displaced off or to be knocked off the target to be deposited on the substrate, right? So you need a minimum of certain threshold energy minimum for you to enable the deposition. So this is the equation for the energy transfer parameter given by your mass of sputtering ion and the mass of the material, M1 and M2. Okay, you can do the calculation depending on the type of material that you want to deposit. So another scope that is important for the deposition is called sputtering yield. So it actually tells you number of sputtered atoms versus number of incident ions. So for every single incident ion incident on the target material, you want to know how many atoms are actually sputtered off the target for the deposition, right? So there are a few factors affecting the yield of the sputtering process. For example, the mass of the gas. So typically we use argon, so it's pretty much fixed. Mass of target materials, this one really depends on what type of material do you use for your sputtering process. So for example, if you have done any sputtering process, you will see there are few settings that you need to key into into the system before you actually start the deposition, right? You can check that out. So normally, if you're referring to our lab, then there's a list of a table of materials with specific settings that you need to key into the system before your sputtering process. Ion energy, for example, your argon gas energy, argon ions energy. angle between the surface normal of the target and the velocity vector of the incident ions, right? So you can see the yield here on the y-axis and the angle of incident with respect to the target material. So that's actually an optimum setting of the target mounting, right? The angle. So if you increase your ion energy, your sputtering yield goes up. So well, it makes sense if you have higher energy of your argon ions. So of course you can dislodge more of the sputtered materials for the deposition, right? So mass of target, if the mass of target increases, your sputter yield will actually go down, right? So this is the relationship you can see. Mass of bombarding ions increase, sputtering yield increase, because you have learned about the momentum transfer. If you have bigger amount of the ions, then the impact will be bigger, right? The impact will be bigger, so you can dislodge more atoms for the sputtering process. So this is a typical sputtering system. So we've seen on the video as well. So you need to have your gas in order to provide those sputtering ions or the plasma. So for example, we use argon to generate argon plus in order to form the plasma. So you need to have your vacuum pump as well, vacuum pump. So in order to be able to pump down the chamber to about -5, so you need rotary, you need diffusion pump. It can be various pump as long as the working regions of the pumps are correct. So then any type can be used. Power supply, in order for you to create a large voltage drop between electrodes or the target and the substrate in order for you to create the plasma, right? So you need the plasma, so you need the power supply to do the job. Else, you'll just have argon gas in the chamber, but there is no initiation of the sputtering process because there is no plasma. Okay, there's no plasma. If you just have gas molecules, so you won't have enough energy to bombard the target material to initiate the deposition. So normally you can tell this by looking at the formation of plasma, or you can actually, in fact, well, you can see directly by the color of plasma. If you don't see anything going on in the chamber, so that means there's no plasma. No plasma means there's no sputtering. No sputtering means that there's no deposition. And finally, you need the target material to be deposited, right? So pretty much this is a schematic of a typical sputtering system. If you use DC sputtering, so that means you need to use DC power supply in order to initiate the plasma formation. On the other hand, if you use RF sputtering, you need radio frequency setup or LC network to be able to initiate the plasma. The rest remains the same. Okay. Right, plasma in sputtering system is a mixture of neutral atoms, molecules, roughly equal number of positive ions and free electrons in the quasi-neutral state. So that's pretty much how it looks like, the plasma through the glass window. We've seen this on YouTube last time. Argon gas is usually used as a sputtering gas because of its chemical inertia to the target material. So what happens, so since we're talking about chemical inertia to the target material, what if you use other gas as the plasma? If you don't use inert gases for your plasma formation, what could happen to your deposition process? What if you don't use inert gas for your sputtering? Anyone? Nabila, what's going to happen if you don't use inert gas for the sputtering process? Why do we need inert gas in the first place? Any idea? Siapa buat sputtering lah? Fazira, why argon? Okay, that's fine. It's all right. Okay, Azika said gas will react with the target, so What's next? If you have gas reacting with the target material, so what's next in the process? You can just continue, Hazika. You can unmute yourself or you can write it down. Gas will react with the target. Okay, that will be the first step. Contaminant. Okay, so what's next? As a result, what do you have? What do you have on your deposited layer? Low chemical reactivity, not quite there. Defect, in what form? So you have a reaction of the gas with the target. So you have contaminant, then what do you have on your deposited material? Higher deposition rate oxide, you will have unintended formation of compound. Maksudnya kalau you ada gas yang react with the material, so instead of katalah you nak deposit ITO, you sputter ITO, and then you want to deposit that ITO layer of say 100 nanometer of ITO on your silicon, then you will end up having ITO plus whatever, ITO plus something else, unintended gas compound, within your film, right? So you won't have pure ITO. So you have ITO something, right? So if you deposit ZAT, you're gonna have like zinc oxide plus whatever, or silicon, whatever, right? Silicon popular. So you have that in your compound. So is that good or bad? Is that good or bad? You want to deposit A and you get B. Good or bad? Huh, Fazira, is it good or bad? Can unmute yourself? Chingwei, is it good or bad? Anyone? It's quite straightforward, right? You want to deposit A and you get B. Good or bad? Is it what you want? Anyone? Anis Shahira, is it good or bad? You want to deposit A, after the process you get B. Is it good or bad? Naim? Naim? Oops, I thought we have connection problems. All right, it's bad, right? Okay. Okay. So in that case, it's bad. You want to sputter A and you get B. Of course, it's bad. Oh, let me start again. Okay. In this particular case, you don't want that to happen. So that's why the gas that used for plasma formation needs to be inert, right? For example, argon. On the other hand, there are cases where you want to use the gas to produce compound on the deposited layer. So let me read. In other cases, there are conditions where you want to where you want to have reaction with the gas. Okay, but the gas is not used as plasma. So that case, we call it reactive sputtering. Reactive sputtering. Okay. Okay, in the default condition, you don't want to have any reaction of your target material with the gas. So, for example, if you have ITO target to be deposited, then you're gonna have ITO target on your silicon deposited. Done. In some cases, for example, okay, let me pick a better example to give you the ideas. For example, you want to deposit silicon nitride. You want to deposit silicon nitride. Okay. Right. You can deposit silicon nitride by default using silicon nitride target in a sputtering process. For example, you use RF sputtering. Then you sputter silicon nitride from your target to be deposited on your silicon. Done. That will be the default way to do that. The second way is to do reactive sputtering. Reactive sputtering means you want your deposited material, your sputtered material, which equals to your deposited material, to react with a gas in the sputtering chamber and form a deposited layer. So in this case, you can do reactive sputtering of silicon target. So use silicon target. You want to have silicon nitride, right? So you use silicon target, but you do a reactive sputtering process with nitrogen gas. So this can also be done. So the first way is obviously to use silicon nitride target, sputter the target, you get silicon nitride on the silicon. And the second way is to do silicon target, and then you have your argon plasma. Then you have another channel coming in, injecting nitrogen gas, and then this silicon will be reacting with the nitrogen, forming silicon nitride to be deposited on your silicon wafer, for example. Right, so you can control the flow rate of the nitrogen, so on and so forth, to be able to deliver stoichiometric silicon nitride on your substrate. Right, that can also be done. So it's either a pure deposition from your target, or it can also be reactive sputtering, right? Depending on what do you need in the layer that you want to deposit, right? So how do we form the plasma in the sputtering chamber? First, a voltage is applied between the electrodes. A breakdown field of gas is exceeded, so you need to know the breakdown field of the gas, for example, argon, creating large number of ions and free electrons. So you use argon, right? So you strip off electrons, outer electrons. So you form argon ions, right? Argon ions plus you strip the electron off, you're gonna have the ions. Electrons from the stripping process are accelerated towards positively charged anode, and ions are accelerated towards negatively charged cathode. Electrons are accelerated much faster due to the small mass. Ions that strike the cathode generate secondary electrons, so you may have secondary electrons as well from the bombardment process. Secondary electrons are attracted towards the anode, so this is pretty much the cycle of how plasma is sustained. At high enough fields, electrons acquire enough energy to ionize neutral atoms or molecules. So the ions generated from the stripping process can also be used to strip off another argon gas to form argon ions and sustain the plasma formation. So this is how it works, right? The cycle of plasma sustaining process. You initiate, and then you want to sustain the plasma throughout the deposition process until the job is done. So in equation, this is how it looks like. You're gonna have like dissociation, atomic ionization, molecular ionization, atomic ionization. This pretty much happens in parallel, right? In parallel, even though you may have some is initiated first, and then at the later step, they are pretty much in parallel with each other, and in order to sustain the plasma. So ionization here means energy is transferred in order to ionize the argon gas. So for example, 15.7 electron volt for argon, secondary free electrons and positive ions are formed after the ionization of the argon gas. Then excitation, so you're gonna have excitation for about 10 to the minus 8 second, returning to the ground, giving emission of the light, right? So that's why you see different colors of plasma depending on the gas that you use. So you can see emission of visible photons in the form of color, for example, this way, right? Slightly purple based on argon. So as I said, you can either use DC sputtering or RF sputtering. So DC is direct current, RF is radio frequency. Apa beza dia? Any idea of the difference between DC and RF? Anyone knows? Anyone? Any ideas? When do you use DC? When do you use RF? DC we normally use for metal deposition. Direct current is for metal deposition. Kenapa metal? We use DC for conductive materials deposition, right? RF, on the other hand, it can also be used for conductive materials like metals, but it's mainly for dielectric deposition. Oxide, nitride, carbide. So you cannot use oxide, nitride, carbide, or other dielectrics on DC. It won't work. There's a reason for that, right? If you talk about aluminium, silver, nickel, platinum, palladium, you can use DC. In fact, you can also use DC for ITO because ITO is conductive. So as long as you have good conductivity of the material to be spotted, you can use DC. If you have a poor conductivity of the material to be spotted, you need to go for RF. So RF is radio frequency. So typically the assigned frequency is 13.56 megahertz. So this is pretty much how it looks like in the RF system. So you have pretty much the same in the chamber. So you have argon gas, vacuum, plates, heaters, plasma. The difference between DC and RF is the way we generate the plasma. So in this case, if you talk about RF, we need to have RF generator and LC matching network. So LC is inductive capacitive matching network, LC network, right? For RF. Untuk DC tak perlu Try to look, what is this LC network? So that will deliver the right power input to the electrodes to initiate formation of plasma in a typical RF system. Okay, so just now I talked about dielectric, right? Dielectric or metals, conductive or non-conductive. So you can generally group dielectric as insulators. Before we go to the next page, it means the same thing, dielectric, insulators. It's referring to the very same group anyway. So if you use insulators without RF, so for example, if you want to deposit silicon dioxide, silicon nitride, silicon carbide without RF, so what will happen is positive ions from the plasma strike negatively charged insulator, so decrease applied negative potential until argon ions are not attracted to the cathode. Voltage becomes lesser and lesser than what is required to sustain plasma glow, and a plasma quenches. So you're gonna have your plasma dies off because if you use if you notice, if you use RF, it's gonna use AC open source. So it is gonna be sinusoidal cycling of your power source. AC network. So you won't have conductive path at this cycle, at the low cycle. You won't have the conductive path of the materials on the target material, because it is insulator in nature, right? So it couldn't sustain the plasma, and the deposition won't happen. If you use insulators with RF, electrons have high energy. This one is pretty much the same, but it has a conductive path to go through. So the difference is mainly on the conductive path. Conductive path, right? So electrons maintain self-biased steady state DC that is potential, that is negative with respect to the VP. Okay, so it has a conductive path on the target material in comparison to the one without RF. Okay, process parameters are similar, right? Except if you work on the RF, then you're gonna have your LC network settings. How a deposition looks like, pretty much we've discussed last time. We have load lock. So kita dah discuss load lock waktu kita discuss evaporation, right? So minimize the amount of air and other contaminants that will be introduced into the process chamber. So normally the process chamber is isolated from the load lock. We don't want to vent the process chamber from -5 to ambient repeatedly, because that will actually introduce more and more contaminants to the chamber. So the way we practice in the lab now is not the best way to do it. The best way to do it is to have a load lock before the process chamber, and process chamber is always maintained at 10-5, and you only have to vent and cycle or reduce the pressure for the load lock before you receive or after you remove the sample. Vacuum pump to bring down the pressure to -8. Well, this one depends on the system. The one that we have is down to -5. Even though we are at -5, so it already introduced so many particles and moisture and unwanted contaminants into the chamber. Every time we vent the chamber back to ambient to be able to get a sample out, right? So it's not good. So if you are working at 10-8, it's even worse, right? It's even worse because you want the ambient to be very pure for the deposition process, but yet you cycle and you vent every single time for the deposition. So that is very unhealthy. Target water heater, power supply. So you see the difference here between DC and RF. So if you have DC, then you're going to have to use a DC power supply. If you have RF system, you're going to have to use RF power supply. So that will make the difference for the deposition process. Ini sama macam saya explain sebelum ni. So these are among the elements. We have discussed all the equations now. So these are among the elements in the chamber during the sputtering process. Right. So you have argon ions, you have glow, you have secondary electrons, primary electrons, the sputtering process itself, and then the connection. Okay, angles of arrival. We have discussed about the line of sight deposition, if you still can recall, when we talk about evaporation process. So it's a very line of sight deposition. So you need to put your samples right on the target to be able to get a good deposition, or else if you go slightly away from the radius, from the center of the substrate holder, then it's going to be poorer in terms of the film quality, even though you can actually rotate the batch during deposition. So it's going to be slightly different on the outer side of the holder compared to the center position. If you compare evaporation to sputtering, sputtering is slightly better in terms of conformity, in terms of the angle of arrival of the atoms or molecules for the deposition. So it's not a line of sight, but then it's not as we're going to see later on. We're going to discuss in part 2 of thin film deposition. We're going to go through a CVD process. You will see later on that CVD is very omnidirectional. Omnidirectional means the particle or the deposition atoms, the deposited atoms are coming from all angles. So we call that omnidirectional. Omni means multiple direction. So that is for CVD. So then if you compare evaporation, sputtering, CVD, we're going to select CVD later on, don't worry about it yet. Evaporation is very line of sight, so that means you need to have a very straight line. Sputtering is always in between, so you have a little bit of omnidirectionality during the deposition, but it's not as good as CVD, but it's not as bad as evaporation. So the worst one is evaporation, is very line of sight. The best one is CVD, is very omnidirectional. Sputtering is always in the center, right? It's a little bit of omnidirectionality, but it's not as good as CVD. So that's a plus and minus points of each deposition process. So if you have a small target or small point source, so wide emitter angular distribution, it follows certain rule of the distribution. For example, if you have a source here with a down here, then it will go into multiple directions, but it will not be as good as CVD. It will not be as bad as evaporation. If you have multiple sources of sputtering, for example, we discussed before about the ZAT487, so where you need to have multiple pockets precursor material, ZAT487 instead of one, in order to ensure stoichiometric deposition process. So you will have more, you have them going into more directions if you use multiple pockets, right? So it follows this kind of distribution, cos and theta distribution. If you have one, then it's going to be slightly anisotropic. If you have a small sample, a small target or small point, it's going to be a little bit anisotropic, even though it has some level of omnidirectionality. If you use multiple pockets, on the other hand, it is more isotropic, so it's more multi-directional. Kita dah belajar untuk etching dulu. Anisotropic and isotropic, and iso is coming pretty much like one direction, iso is coming from all directions. So large targets or multiple pockets are more omnidirectional in nature if you compare to a single target, right? Better step coverage than evaporative deposition, but worse than CVD. Okay, so if you talk about the deposition on features, katalah you ada pyramid ke, you ada trench like that, macam yang kita tengok on the slide. So more omnidirectional than CVD, than evaporation, but it's worse than CVD. So if you want to compare the step coverage of the deposition, CVD is better than sputtering. Kita akan belajar CVD is better than evaporation in terms of step coverage. Maknanya it covers features better, right? CVD is the best, sputtering between, evaporation is the worst, right? So remember, like last time I shared about my previous work on textured glass. So some areas are thinner than the other areas. So these are the arrival angles. Step coverage problem. Wide arrival angle distribution, poor bottom coverage. If you have a wide arrival, some may end up on the shoulder of the features, and that's it. It's gonna block. It's gonna be a shadowing effect for the upcoming arrival atoms, because it's being blocked from filling the trench, right? So if you have narrow arrival, it's gonna be better on the bottom coverage. So there's always a plus and minus of the deposition. Lack of directionality means filling of high aspect ratio trenches and vias difficult. So trench, selalunya kita panggil structure ini trench atau via, lubang ni, trench or via. We're gonna see later on. When we talk about interconnects, you're gonna see more vias. So these are all vias. So filling in will be very difficult. You can introduce some annealing process after the deposition if you can, or in fact you can also do substrate heating, if you can remember substrate heating. TS punya setting kan, substrate temperature is actually a heating process. You can do heating while doing the sputtering process to minimize this problem, because when your atoms arrive on the structure, they pretty much landed and stay put, and they don't go anywhere else. If you put some level of substrate heating, some extent of substrate heating, you can actually manipulate the landed atoms so that they can move a little bit to a more to a better position, right? To a better position. So that will actually change the problem that you see here. So that can minimize the problem, because if you can move the atoms that are landed on the features, so you can actually play around with the conformality of the deposition. If you don't use any heating, then whatever landed on the features will stay there forever. Okay, so annealing can be done to some extent. It can help. Same thing, right? This one is the coverage problem that we've seen just now. You can also vary things. You can change the argon pressure to be able to change the deposition process. You can, in fact, use higher pressure. For example, if you do your process at 5 millitorr, mula kita pump down to about -5, base pressure, then you inject the argon, so you're going to increase the pressure to about -3. So this is like 5 times 10 - 3. So you can, in fact, vary the amount of the pressure, 5 millitorr or 7 or 3 or whatever millitorr, in order to change the deposition process. So if you go for higher pressure, for example, by injecting more argons, so you introduce more collisions of the argon atoms in the gas phase, and then that will result in shorter mean free path. So we've covered mean free path last time while discussing about the vacuum level. So you induce shorter mean free path, which will induce more isotropic deposition. Okay, sebab dia ada banyak collision, so dia ada banyak collision, dia macam is going everywhere. So going everywhere will help to introduce a more isotropic deposition. So that doesn't mean if you introduce higher pressure is bad for the deposition. It depends on what you need on your deposited layer. So last time when I was in Fuji and we did the development of the 1 terabyte, some processes we use higher pressure in order to do this, in order to induce shorter mean free path, so that you have a better deposition in terms of the isotropic nature. Then you can improve certain qualities or certain performance, certain parameters in your device. So to say whether it's always good to have higher pressure or lower pressure, there's no generic guideline. It really depends on the process and what parameters are you looking for, right? Heating can improve planarization in some case. This is the thing that I mentioned now. If you induce heating, you can still manipulate the final position of the atoms or the molecules landed during the sputtering process. If you don't put anything, that will just land it there and then stay put forever. Okay. So reacting is what we discussed now. So you can either do, for example, silicon nitride deposition by using silicon nitride target, or you can also use silicon target plus nitrogen gas in order to form silicon nitride. When I did my PhD last time, silicon nitride is one of the layers in the device. So the best silicon nitride layer was obtained from reactive sputtering. It's not from the pure silicon nitride target sputtering, but instead a mixture of silicon and different flow rates of nitrogen gas to form the final silicon nitride optical layer. Right, so reactive gas is introduced into the sputtering chamber in addition to argon plasma. So plasma is still based on the argon. So you still have the same argon, but instead you just have another channel coming in, injecting nitrogen, for example, if you want to deposit silicon nitride, then reacting with silicon target to form silicon nitride. So another example here, you can do titanium nitride by sputtering titanium and then reacting with nitrogen to form silicon titanium nitride on the layer, right? So reaction occurs at the wafer surface or on the target itself. TiO2 reactive sputtering. You can deposit TiO2 or you can also deposit Ti with oxygen gas to form reactive sputtering. Controlling the stoichiometry of the reactive sputtering sample is sometimes difficult. Stoichiometry means, apa maksud stoichiometry? Anyone? Controlling the stoichiometry of the reactively sputtered films is sometimes difficult. Say, apa maksud stoichiometry kat sini? If you want to deposit silicon nitride. Anyone? Anyone can tell what is stoichiometry here? What time is it? 12:49 already. So let's go for 2-3 minutes. Amira, anything on stoichiometry? What is the stoichiometry here? Apa maksud stoichiometry? Ratio of, okay, Hazika, ratio of, right? If you say silicon nitride, then ratio of what? Yes, good. Silicon and nitrogen. You want to form silicon nitride with certain ratio. So for example, if you want to have 50-50, then it's going to be like silicon, you can write it down as this one as well, SiXNY, right? 0.5, 0.5, or 0.3, 0.7, 0.8, 0.2. So that is the stoichiometry. So if I say I want a stoichiometric deposition, well, usually I'm referring to 50-50 or 0.5, 0.5. In some cases, different ratios work better in your device. Say, instead of 0.5, 0.5, you may see that 0.6, 0.4 works better for your device. And it's like, it's not a generic, there's no a generic rule for the stoichiometry rule, but instead it depends on the device, right? So if you say silicon nitride for optical layer, then normally you're going to measure refractive index and extinction coefficient as the parameter to show the quality of your layer, right? Refractive index and extinction coefficient, if you're talking about optical material. So it depends. So for example, if you want to have like certain level of certain value of N and certain value of K, you can actually alter the values by altering the stoichiometry of the deposited layer, X and Y, right? Magnetron, so I think we'll just stop here. We still have magnetron, biasing, finish. Okay, we'll continue this tomorrow. Tomorrow we're gonna continue with a magnetron sputtering and the rest of the topic, and then we'll move on to CVD as your second part of thin film deposition. Okay? Any questions? Right, no question. I'll see you tomorrow then. Okay? Bye-bye. Assalamualaikum.